Okay, welcome back. Good news is on Thursday, we'll have basically a little bit, one more module to take a look at. And then the second one will be applying everything we've learned about probability. Again, we're not becoming experts at probability, but we're getting enough so that we can use it for statistics. Okay, so this is what we were talking about on that last slide. If there's an or probability, we have to decide whether the events are mutually exclusive or not. And we'll take a look at why that makes a difference. Mutually exclusive means that two events cannot occur together, something like raining or not raining. You can't not rain and rain at the same time, right? So there's some things like that. When you're rolling, well, we'll get into some examples. However, so that only can happen when A and B, two events, have no outcomes in common. So that would be a sample space that looked like either A happens or B happens, but they don't happen together. There are some events, however, where either A happens or B happens, or they could both, there's an overlapping area where they could both happen. So think about like drawing a card. You could draw a red card, or you could draw an ace, but there's the ace of hearts and the ace of diamonds that are both red cards and aces at the same time. So there's some things that where we get this overlap, and we'll look at a little bit. But the reason this is so important is looking at this picture is the easiest way to look at. If we count everything in A and everything in B when they are not mutually exclusive, what have we done to this intersecting area? How many times have we counted that middle piece? Twice, right? We counted it for A and we counted it for B. So it got counted twice. We're going to have too much stuff, right? Our numbers are not going to be right. So the formula we'll see, we'll subtract it off once. So the way we do is forward, we count everything, but we know we're counting something twice, so we subtract it off at the end. If they are mutually exclusive, there is no overlap. We don't have to worry about that. That's the easiest case, is we're going to add the two together, right? Either A or B happening makes sense there. You see the picture. Well, the probability of A plus the probability of B would be for one of them to happen or both of them to happen. Okay. So how about if I roll a die? They show two dice, but when they say die, die is singular. Dice, D-I-C-E, is plural. So if you say die, it's one die, although the picture shows two. So I just realized that today. Rolling a 3 on a die or rolling a 4, is that mutually exclusive or not? Could you roll both at the same time? No, not with one die, right? So these are mutually exclusive. So the way we would calculate that probability is we just add the two probabilities together. So probability of getting a 3 is 1 out of 6. Probability of getting a 4 is a 1 out of 6. And because they don't say it here, but if we were considering the or probability, it means add them. So there are now 2 out of 6, which is 1/3, 33%, right? Okay. What would it look like for something to not be mutually exclusive? Well, here we're randomly choosing. Event A is to select a male student from the class. Event B would be to select a nursing major. Are those mutually exclusive? Could they not happen together? Or could they happen together? Could you select someone who's a male student and a nursing major? Sure, we could. So these have some overlap. These are not mutually exclusive. So when we were doing our counting, anyone who was a male student who was a nursing major would basically get counted twice, and so we would need to subtract them off. So we'll see how this works in just a moment. Here's the formulas. Probability events A and B will occur. Probability of A plus the probability of B, like we've done before. If they're not mutually exclusive, and even if they are mutually exclusive, we would subtract, but if they're mutually exclusive, probability of A and B happening together is 0, so you're always think there's this subtraction that goes on, and that will give it. If they are mutually exclusive, we don't really have to think about it because we're subtracting 0. So it just makes the calculation that much easier. So if you can identify and say they're mutually exclusive, I just need to add them together, good. If they're not mutually exclusive, we have to remember to subtract off that overlap because it's getting counted twice. And we'll show you in a couple examples here exactly why that happens. And remember, this only goes for the probability of A or B. So always look for those words, A and B. Remember, that's when we're multiplying them because it's this and then this. That's the multiplication principle. The or is the addition principle. It's the only one we add, and we have to look for mutually exclusive. Okay, so let's see. You select a card from a standard deck. Find the probability that the card is a 4 or an ace. So 4 or an ace, are those mutually exclusive or are they not? Is there a card that's both a 4 and an ace at the same time? No. So they are mutually exclusive. So when we calculate this probability, we don't have to, there is no overlap. There are 4 aces, or sorry, well, yeah, there's 4 aces out of 52 cards. And there's 4 fours out of 52 cards. And so the probability of getting an ace or a 4, we just add them together. It's 8 out of 52. And then you could turn that to a percentage. But that's how we do that calculation. Okay, we didn't have to worry about the overlap. Questions, or that's okay. How about you roll a die, find the probability of rolling a number less than 3, or, right, the or. So pick that out. So again, I'm mostly talking to myself right here because I overlook those things. Or rolling an odd number. Now, is there any overlap for that? What are the numbers less than 3? 1, 2, right? Are either of those numbers odd? Yes. 1 is both less than 3 and it's odd. So if we're not careful, we would count 1 twice, right? We would count, okay, how many numbers are less than 3? Well, 2 out of 6. How many, or rolling an odd number, how many odd numbers are there on a dice? 1, 3, 5. That was 3 numbers out of 6. And if we just stopped here, we would say that's 5 out of 6. That's a pretty good chance. But we counted one of the numbers twice, didn't we? We counted 1 for the first group being less than 3. We also counted 1 as being an odd number. So we just have to say, okay, I counted 1 twice, so let me subtract it off, so I only counted once. Okay. And I'll tell you, there's 2 ways to do this. You could use the formula, which is helpful to remember because some things that's the easier way to do it. Or you could just be very careful when you count. I could have said, well, numbers less than 3 are 1 and 2, so that's 2 out of 6. Then when I go to count the odds, I could say, oh, wait, I've already counted 1, so let me just count it once. The odd numbers that are not 1, 3 and 5, are 2. But what you'll see is you'll get the same thing. This is 5 minus 1 is 4 out of 6. Okay? So the diagram kind of shows it. If you just add the 2 together as it is, you're going to count something twice, subtract it off, and you're all okay. Or be very careful about what you're counting and how you're counting it. Don't count it twice. Just make sure you count everything once. That's another way. With smaller groups, to me, that makes more sense. I go through and I would say, well, I got 2 out of 6 for being less than 3. And then there's 3 numbers, but I've already counted 1, so I would go 2 out of 6 again. And I would still I'd get the right answer. So, but I wouldn't have to do the subtraction. Okay. But you're going to see sometimes we get to some things where the way they give us the information, it might be easier just to subtract their overlap because we might know what it is. Something like this. Okay. So we've got a frequency distribution. Shows volumes of sales in dollars and then number of months in which a sales representative reach each sales goal. So sales volume, this is 0, almost 25,000. For 3 months that was reached, 5 months, and so forth. This was probably 9 times. So mostly they're selling between 124 and 125,000. Find the probability that the sales representative will sell between 75,000 and 124. So 75 starts here, 124 ends here. Now, they're using the word and here in a different way to say that we're looking at these two groups. And really, what we're looking is that they do, you can't do both of these at the same time, right? So it's really kind of a question of an or. So we know 75 to 99 is 7 out of a total of, how many months are represented here? See, there's 8, 14, 21, 30, 35, 36 months, if I get that right. If not, adjust my number down here, right? So there's that probability. And then going from 100,000 to 124, that happened 9 times. So we would just add those two together. They are mutually exclusive, right? You're either in one band or you can't be in both bands at the same time, because you can't be in here if you're in here, and so forth. And so 7 plus 9, 16 out of 36, which again, I'll let you can reduce, you can turn it into a percentage, but that's the basics of probability counting and dividing, okay? Sometimes we have to be careful about it. Again, they're using the word and, but that in this case, it doesn't mean to multiply, because it's this group and that group. They're talking about two different groups, okay? And the way they use it in probability, you can't be in both, since they're mutually exclusive, you can't be in both at the same time. Both things could not happen at the same time. Okay. A blood bank catalogs the types of blood, including whether it is Rh positive or Rh negative, given by donors during the last 5 days. The number of donors who gave each blood type is shown in the table. And then now we're finding the probability the donor has type O or type A. Okay, so this is a probability setup. This is an event, type A, O, or type A. Is that mutually exclusive? Yeah, because you can't have there is no OA blood type. You can't be both O and A at the same time. Sorry. You're either O or you're A. And so the probability, you take and it's not talking about positives or negatives. We could take the total of O, the total of A, and we could add them together, divided by 409. So there's 184 out of 409 is the probability for being an O, plus 164 out of 409 probability of being a type A. Add them together. 4 and 4 is 8. 8 and 6 is 14. Carry the 1. 348 out of 409. And again, you could turn it into a percentage if you like with the calculator, but that's the counting process, right? There is no overlap. Find the probability the donor has type B or is Rh negative. So type B is here, and you'll see what I mean by Rh negative is right here. Is there any overlap? Yes, right there. Now, the way to use the formula is we would say, okay, calculate the way of having type B. That would be 45 out of 409. Probability of being Rh negative is 65 out of 409. Oops, we counted the 8 twice, didn't we? We counted it with the B, we counted with the Rh negative. So we don't want to get too quick here. Don't want to go to equals yet. We want to remember to subtract off the 8 out of 409. Okay. Now again, you could have, when you got the Rh negative, say like, oh, 65, but let me subtract 8 so I don't count it twice. Again, multiple ways to do it, but just make sure that 8 does not get added into the system twice, which if we stopped with the plus, that would do it. We subtract the 8. So this is 110 minus 8 will be 102 out of 409. Okay, so with tables, it's generally fairly easy to see whether they're mutually exclusive or not, depending upon what they're asking for, whether we're going with all columns or all rows. If we go with a column and a row, we always have that overlap, that piece in the middle. Okay, so again, the mathematics of it is easy. We just count and divide, right? Count how many in there, divide. Sometimes we're adding when we're doing OR probabilities, but the difficulty is what do we count, right? And so we have to see that if we're not careful, we end up counting the 8 twice. On the other ones, we didn't have to be careful because we were just dealing with two columns. So there was no overlap here. Here's O, here's A. There is no overlap, so we don't have to subtract anything off. Okay. Yeah, they go through it. This is just a summary of what we've talked about so far. So like for your note sheet, this might be helpful. Again, you could copy and paste it into your note sheet when we get to the test. That's fine. Or just make it, handwrite it or whatever you need to do. Some of the things you might remember, like this rule of subtracting 1, when you have a not, but if not, put it in there, right? So if you can go through and the best way is when you're going through the homework, what do you have to go look up? If you have to go look something up, make sure you put that on some notes somewhere. If you don't have to look it up, it means you've internalized it and you just got it. And sometimes having notes about it would just kind of get in the way. So anyway, the rules of what we've done so far. So let's do one last application. Use the figure to find the probability that a randomly selected draft pick is not a running back or a wide receiver. So you see all this data. Do we want to count all the not linebackers, running backs, or wide receivers? That'd be a lot of counting, wouldn't it? So what if we count the number of running backs and the number of wide receivers? That's only 2. We could add those together because it's an OR probability. And then we want that to not happen, so we subtract that from 1 or subtract it from 100%. A lot easier than trying to count everything else. So, and what we see is wide receivers are here. There's draft pick. I guess these are number of draft picks. So there's 37 wide receivers that were in the draft pick. What else are we looking for? Running backs. Running backs. Where are the running backs? Here's the running backs. There were 16. So we know there was 37 plus 16. The hard part is we don't have to add these up because they told us up here. Sometimes they give us the information that we don't have to go and add it all up. 255 total. So if we went and added all these numbers, we'd see it's 255. But then we have to remember, we don't want this. So that's what I mean is the words. The OR tells us to add the 2 together. The NOT says subtract it from 1. Okay, or 255 over 255, right? Because you need common denominators. So we do that. 37 and 16 is 40, 52. 255. And then we subtract that from 1, which is 255 over 255. And that gives us 203 out of 255. We would have gotten the same results if we went and added all these other numbers together, but I don't know about you. I would rather just not have to add all these numbers together. I just add those 2 and subtract it from the 255. Okay, so that's using that property. Again, on an exam that similar to something like this, I did it the long way. Spent 15, 20 minutes, whatever it was, and I realized I could have done it a lot quicker and used less brain cells and had more energy to do the other things. So think about that. So those, again, probability is pretty simple in the fact that we just count and then we divide, but we notice that we have to watch for a little bit of ways that the question is worded as to whether we're adding, whether we're multiplying, whether we have overlap. And tomorrow we pick up something called conditional probability. So that's going to be, we know a little bit about the situation first. We know what something happened. So there's a condition that we know about, and we'll see how that affects our counting. But the probabilities are all the same. Number of in the event divided by the total. It's just what we're counting that changes. Okay. Excellent.